And he's an assistant professor in mechanical engineering at the University of Michigan. And he also has appointments in the University of Michigan Transportation Research Institute and the University of Michigan's robotics program. He received his PhD in electrical engineering in December 2012 from the University of California, Berkeley. And his current research interests include dynamical systems, optimization, and robotics, especially to applications involving human interaction with cyber physical systems. So now please join me in welcoming Professor of Vasudevan.
So thanks for the introduction, and thank you for having me here. It's a pleasure to be back in Berkeley. It's fun walking around with nice weather and whatnot, so thank you. So I'm going to talk a little bit about certified control of autonomous systems using infinite dimensional optimization, but with a title like that, with that many nouns, it's usually worthwhile to start off with a few pictures. So the first thing I'm going to do is actually, well, if I can start this off, see if this works. No? Okay. So I always like to start off with this chart. So everyone's really excited about autonomous vehicles. They think this is the future. Everything's going to be solved with automation. I like to at least give us some grounding on this front. So on the y-axis here is the number of fatalities per 100 million miles traveled in the US. On the x-axis here is data from NHTSA per year on the number of fatalities. So what you can see on the top left here is that we're about at 25, and it's in 1920. So 25 fatalities per 100 million miles driven. You go all the way down here, we're about at 1 fatality per 100 million miles. So in short, humans are amazing drivers. Fantastic. Okay? And in part, that's due to us. As engineers in this room, we can take credit. The latter part of this talk, it's going to be harder for us to take credit about autonomous vehicles, but at least this part we can take some credit. So some of this is obvious and sort of starts off in sort of industrial engineering research where we start thinking about things like adopting traffic lights or a speed limit. These things seem obvious in retrospect, but when you drive in a third world country, you realize that those things are not so obvious. You start moving over, you start getting inside of the car, so seat belts, airbags, and then we start getting into the harder control problems that I'm going to speak a little bit about today. Anti-lock braking systems, electronic stability control, and we slowly start seeing the effect of diminishing returns here. It's really hard for us to build systems that actually reduce the number of fatalities. Okay? So, we talk about these numbers. Everyone in Silicon Valley is very excited about this. This is all of the United States, and people want to try to think about using autonomous vehicles to reduce this number by quite a bit. So let's try to ground ourselves by looking at some real data. Okay, so this is Google. They've been driving since 2010. This is mostly in Mountain View in Arizona. And you start off here in May 2015. This is their total accumulated driving. They're about at 1.5 million miles. I think now it's been about a year. They're probably closer to 3. Okay? We're not even close to having enough power to be able to really validate the performance of these autonomous vehicles. If we're just going to sit there and drive these cars around, it's going to be a really long time before we can actually verify that these systems are going to perform correctly. Okay? And again, this isn't Michigan driving. I'll show you what Michigan driving looks like in a little bit. This is driving in pleasant weather. Maybe not so pleasant this winter, but usually very pleasant. So as a result, we've seen sort of these scary headlines pop up. So Uber, they've been driving not for so long, but they've been driving in more interesting places, arguably. They've driven, and this is from last month, about 20,000 miles total, and they've had a human have to take over every mile. Actually, the number is 0.8 miles. They've had to have a human intervene in the operation of the vehicle. Okay? Google just recently got into an accident, and it was their fault. Okay? So we're thinking in our minds, hey, this is a really hard problem, but actually we really need to think about this even harder. They're driving in great places, and in fact, they're driving really slowly. So in fact, they're driving so slowly that they got a ticket for driving too slowly. Okay? So this is really hard. And in fact, arguably, the challenge here is not just a perception problem. So many of us have been thinking about this as something like, hey, deep learning will come to the rescue here. We'll collect lots of data. We'll learn what a car is. We'll learn what a human is. In fact, I'd argue that this is a planning problem as well. That is, driving slowly here is not just an effect of having to interpret the signal that's coming in from sensors. It's also a problem of having to think about control design and thinking about control design in a way where we can prove things about the rate of operation and the correctness of the controller at the same time. And the example I'd like to point to is this one here. So Google was driving along. they came to an intersection, they were actually following the rules of the road. They slowly pulled out of the intersection as they normally do. And they were actually ran into. And it was because they recognized the car coming at them, but they couldn't design a controller quickly enough to actually drive through the intersection fast. So by being conservative, by not being able to plan effectively, they're basically sort of tying their hands behind their back. And in fact, what I'd argue here is that planning is a really hard problem in general when you have high-dimensional systems. So when I was at MIT, I worked on this project. This is our robot. Okay? And what you see is playback at about 20 times real time. And what you'll see is basically the robot walking around, pausing for a really long time, and then making a quick plan and then replanning. Okay? And in fact, this is a lot like the self-driving car problem. Models of cars are actually fairly high-dimensional, especially when you incorporate things like friction. And in practice, trying to develop plans in real time is really challenging. So many people who are watching this from the audience said, hey, why does the robot just stand there and stare at the world for so long? And part of the problem here, again, is that figuring out what's going on with the sensors is a challenge, but designing plans is really hard to do efficiently. And in practice, again, self-driving cars need to be able to operate very quickly. Okay? If I'm going to stop there and think about replanning at every step, I'm going to be stuck in the middle of this intersection forever. Okay? And we really do need to think about how do we operate? Do we operate and design controls quickly enough? The deep learning guys and the computer vision guys, they're going to answer the questions about perception. But we in the controls community need to start thinking about how do we answer the real-time control design question while certifying the performance of the controller. And that's what this talk is really going to be about. Can we answer this challenge? And in practice, let's see, we need to take a step back here and think about the way that autonomous controllers work for autonomous vehicles. So the high level, there's a controller that basically does route planning. So it's saying, hey, I want to get from Berkeley to SFO, and it designs a path. So that's something that Google Maps or MapQuest, if you're a little bit older, you can solve. At the mid-level, you have this thing that does trajectory synthesis that basically solves some sort of problem that basically decides how you go from this intersection corner to another intersection corner. Okay, and then at the low level, you have basically the engine itself, or the powertrain system. And in this instance, what's going on is that usually the trajectory synthesis is done with a fictitious model, meaning a simplified model of what the car is actually capable of doing. And it generates something like a velocity profile or a torque profile that's then passed into the low-level path follower, which then tries to actually follow that path in a reasonable way. Okay? So the focus of this talk is really going to be about these two pieces here and how they talk to one another. Can we start thinking about ways that we can prove theorems about bounding the rate of operation while certifying the correctness of the controllers generated? And in particular, the question we really want to answer is, what's the relationship between these two? That is, if the trajectory that's being synthesized by this low-level model is using a kinematic model of the car, well, at the end of the day, it's generating some sort of velocity profile that's then passed down to this low-level path follower. But the low-level path follower cannot follow that kinematic path perfectly. So let me explain. I'm driving along in my kinematic path following algorithm, of my car. What that means is I can instantaneously change my velocity or change my heading. My real-world car actually has mass, right? And as a result, it takes it some time to actually be able to achieve that velocity. Okay? Being able to understand the relationship between these two steps is going to be critical to us being able to certify the correctness and the real-timeness of any controller that we want to generate. Okay? That's what we're going to discuss. And it's worthwhile for a moment to take a step back and see what others have done in this space. Again, since this is such an important problem, this is sort of the hierarchy that every autonomous vehicle uses, we need to understand why these two hierarchies have been thought of and how they interact with one another. And so the things that I'm going to sort of think about here is the method, obviously. The next thing is trajectory synthesis. So I have my low-level controller and my high-level controller. Well, my low-level controller is going to try to follow that velocity profile as best as possible, but how is it going to try to do it? And can it optimize over the safe set in some way? I want to be able to certify the performance of the controller in the presence of uncertainty, specifically the fact that I may have a kinematic versus dynamic model, and I need to be able to relate these two. And then finally, I really want to be able to to develop this mechanism in a place where I'm now presented a new scenario and I can resolve that new scenario efficiently. So, sort of several different algorithms out there. RRTs are a popular one in the computer science community, and many people use them in autonomous vehicle today. So they're able to do things like optimize over some sort of trajectory space by simply sampling. They have a challenge in certifying the performance of the controller because they're just sampling in the space of trajectories. But the good news is that they can work efficiently, meaning that you can run this Monte Carlo method on a GPU and maybe find a solution. Okay, but this gap of being able to certify the performance under uncertainty is really an important thing for us. Again, because we are not going to be able to drive our cars over hundreds of millions of miles. So it'd be really useful if we could actually certify the correctness of our controller. The next methods are sort of these MPC-based methods. So MPC is model predictive control, and the way that these methods work is basically by solving usually some type of linear program or quadratic program, where they try to generate a controller using a linearized model of the vehicle. So Francesco Borelli here has done some beautiful work in this area, and I've had the good fortune of working with him. And in fact, these methods work really well when you actually hand a trajectory to the MPC method and then are asked to follow that trajectory. They struggle to certify the performance under uncertainty, and they're able to work in real time. I'll show you a few examples here. So this is an experiment. This was my first time in Michigan, by the way. This was in 2010. I was a graduate student here. I was working with Francesco and Ford. And what we were doing was driving this car and trying to synthesize a controller in real time that could avoid obstacles. Okay, we're running MPC here. And let me turn up the volume now. Everyone sort of hear that? Okay. So this is when MPC works. This is when MPC doesn't work. Okay, so that was us running into a snowbank. The problem was that we generated basically a path that we were following using MPC, and unfortunately we were outside of the regime where the linearization was valid, basically because the student had turned on the controller a little bit too late. That wasn't me, by the way, but it is someone who works at Tesla now, so there you go. Okay. He's actually fantastic, by the way, so I would trust his controllers. In any case, this is hard to do, and again, we want to really be able to certify these things because we're not going to be able to say, hey, MPC method, I hope you work, and I hope I can test you across 100 million miles. That's going to be impossible for us, so we really want a method where we can certify the performance under uncertainty. There's these methods called zonotopes. They're actually quite beautiful, but again, for these methods, you really do need a trajectory handed to you. There's these methods, again, that we've played around with and that Claire and John Ligouros and many others have used using the Hamilton-Jacobi-Bellman equations. They can do a version of trajectory synthesis. It tends to require the addition of a new state, usually. They can certify the performance under uncertainty. It requires basically formulating a really hard min-max problem, but they don't really work in unknown environments because basically every time I see a new environment, I have to resolve the problem in order for me to really be able to say anything. And these methods take quite a bit of time, usually. Okay. The last one is this idea called funnel libraries. It's one that I was affiliated with when I was doing my postdoc at MIT. What it does is basically generate several different linearizations of a nonlinear system, and then find the regions of attractions for those several different linearizations, and then you switch between those linearizations. It can sort of manage the uncertainty between that kinematic and dynamic model, but not really, and we'll talk about why in a little while. But it works well in unknown environments. The danger is that it doesn't really synthesize a new trajectory. You have to sort of do that a priori, and that can be hard to do in practice. So this method is going to talk about a method that does all three. Okay? So that's going to be the goal here. And what I'm going to do at the beginning is I'm going to talk about this middle bracket. Okay? I'm going to talk about how can we certify the performance under uncertainty. And in particular, I'm going to talk about a representation of a set that is going to make the trajectory synthesis then easy. So in that way, I can sort of balance out the two. And what that means is that when I have a nice representation, I can do the trajectory synthesis and the unknown environments as long as that representation is nice. And that's what our goal of this talk is going to be. And this is very much a 2 words. So we're not done yet, but this is something that's taking a step in the right direction. Okay, so that's going to be sort of the 2 pieces I'm going to speak about, and then I'll conclude. Okay, so let's think about this problem. So I have a car in the world. Okay? The car has some dynamics. Okay? It has a state, maybe some high-dimensional state. This is the powertrain model of the car. And the state belongs to some set, D, and it has some input that at each instance in time belongs to some input space. Okay? In addition, I have a kinematic model of the car. Okay? You don't have to think about it as kinematic, but simply a lower dimensional model of the car. Okay? This low dimensional model of the car evolves in some lower dimensional or some subset of the original state space. Okay? And now what I'm going to do is introduce a parameter here. That parameter k is basically going to describe the way that a high-level trajectory planner works. Okay? So it basically is going to try to optimize over some sort of parameter set, maybe some sort of velocity profile, that it can then hand to that low-level controller in order to try and follow that low-level control design. Okay? So this is my model. Okay? And now that parameter space is actually going to live in some set capital K. Okay? And in practice, this could be something like the steering and acceleration broken up into two different parameters. And in fact, as I choose different parameters in this space, I'm going to get different types of trajectories, right, in the real world. Now the problem is there's a gap, right, between trajectories designed for this system, Fs, and the trajectories designed for the higher dimensional system, F. So one way to think about this is, I could have a unicycle model of a car. So this is pretty close to, sort of a simplified dynamic model of a vehicle. Okay, and on the right-hand side, I can have a Dubin's model of a car. Okay, so the left-hand side one, notice that theta double dot and v dot are both states, or theta dot and v are both states of my system. So in this instance, I get to control them. So I get to choose my rate of steering, or my derivative of my rate of steering, and I get to control my acceleration. And on the right-hand side, instead, I basically get to choose K1 and K2. So K2 here is a velocity, and K1 here is a steering rate. Okay, and there's a gap between these two systems. To see that gap, let's start off with the system on the right. So it chooses a certain velocity profile. It chooses a certain rate of steering. And in practice, this generates a trajectory like the one drawn here. But in fact, if I try to follow that trajectory, maybe I use some sort of PID loop. This is typical. In this instance, I'm not able to achieve that steering rate right away if I started off with my steering pointed straight forward. So there's a gap. It takes me some amount of time using my PID loop to converge to that actual steering rate. So in fact, this gap is what I'm going to try to hold on to and understand. And the way that I'm going to try to do that is by bounding the difference between these two systems using these curves that are drawn in purple here. Okay? And in practice, what I know is that my unicycle model is not going to behave arbitrarily. That is, if I hand it some sort of velocity profile it should try to follow, it's going to try and use some sort of PID loop to try to track that as best as possible. Right? So it's not going to behave arbitrarily. It's just going to have something like a little bit of delay before it's actually able to achieve that velocity or that steering rate that I wanted to command. And what we want to try and understand is really how this delay affects our system. Okay? Let's go back to our models here. What I'm going to do is I'm going to introduce a G term here. And this G is basically going to correspond to that magenta curve that I described earlier. Okay? What I'm going to do is try to hold on to this and introduce a disturbance term that's going to describe the gap between what I want to command into the system and what I'm actually able to get out from the system. And in practice, I want to understand the upper dimensional system, that is F, using the lower dimensional system, that is F of S, okay, with this G term added onto it. And the way that I'm going to do that is by introducing, first, this capital F system so that I don't have to carry around so many terms. And the next thing I'm going to do is talk about sort of the reachable set of the system. And in practice, this reachable set is going to be drawn in green. It's all of the different things that are reachable beginning from that initial condition under all of the different values of K. Okay, so if I understand this set basically describes the difference between my upper dimensional system and lower dimensional system. So if I select a particular K, what that's going to correspond to is some sort of slice of this green curve. Okay? And that slice is basically going to tell me what is achievable by my lower dimensional model using this higher dimensional model with disturbance. Okay, so this is this reachable set, DFRS. And in practice, what I'm going to be after is a nice representation of DFRS, because what's going to end up happening is I'm going to start putting in obstacles and things like environmental restrictions in real time. And as long as I have a nice parameterization for DFRS, what I want to be able to do is use that nice parameterization to be able to do intersections and find the safe set of gains. If I can find that safe set of gains, then I can then do optimization directly over that safe set of gains in order to ensure the safety of my system while doing real-time planning. So in fact, that's going to be what we try to do in this part of the talk. So I'm going to compute a representation of this forward reachable set offline. And that representation, I want it to be nice enough so that when I intersect it with obstacles in the real world, I can find a safe set of gains in real time. And then I'm going to optimize directly over that safe set of gains, and I'll talk about how that works in more detail in the second portion of my talk. So the way that I'm going to do it, so computing DFRS is very hard. And finding a nice representation for it is really hard, that I can then do optimization in a nice way. So the way that I'm going to do that is by introducing an object called occupation measures. So for the sake of this discussion, on the x-axis here is time. On the y-axis here is basically some abstract version of my state space along with my disturbance space. And what I'm going to do is consider a trajectory here of my system. Okay? And I'm going to introduce this novel notion called an occupation measure. Okay? So an occupation measure is going to be the integral of some set S given xs and d. So in practice, if this is the set S, we'll notice that the trajectory passes through this set. So in fact, if I integrate that function up there, use the laser pointer now. So if I integrate this indicator function on this set, we'll notice since the trajectory passes through this set, this indicator function will be non-negative. So in fact, the measure of this set, given xs and d, is going to be non-negative. Versus here, the trajectory doesn't pass through this set, so this measure is going to be 0. So what this measure is doing is it's evaluating the amount of time that a trajectory spends inside of my set. Okay? So in a similar way, what I can do is define a terminal measure that lives only at this terminal time. And what it does, again, is given xs and d, it creates a set here and sees if my trajectory passes through that set. Okay? So the great thing about these measures is they're really going to be useful when I try to describe the evolution of my system, and we're going to see that in a moment. But in order to do that, I need a few more definitions. So the first definition is going to be a lead derivative. Okay? So I'm going to denote the lead derivative by LF, and it's basically going to be defined like this. If you've never seen a lead derivative before, this is what it is. Okay, and I'm going to define an adjoint operator to this lead derivative. This adjoint operator is defined this way, where basically I have a dual pairing between LFV and mu, and I scoot this over by defining an adjoint, and I get this L prime of f. So this guy, this lead derivative acts on functions. This lead derivative, or the dual to this lead derivative, acts on measures. Okay. So what I'm going to try to do is construct this nice representation for DFRS by lifting my ordinary differential equation into the space of measures. And what's going to happen is, despite my dynamics being nonlinear, I'm going to get a linear equation over the space of measures. And that linear equation over the space of measures is going to be amenable for me to do computations with and generate a nice representation. So the first thing is this theorem. Okay? So suppose I have a solution to my dynamics under a disturbance beginning with x naught and k. Okay? So then these measures, this occupation measure and this terminal measure, satisfy this equation for all continuously differentiable functions v. So what this does is basically it allows me to summarize the behavior of the system using a nice equation that's linear over measures. Now the penalty I pay is that I have to check this equation for all continuously differentiable functions, but the benefit I get is that this is a linear equation over measures. And linear is always good. Okay, so we want to hold on to this object and try to understand what we can do with this object, and I'm going to describe that in a few slides. Okay, so for compactness' sake, whenever I have an equation that's true for all functions, I'm going to write it this way, because then it's just an equation over measures. So the question now is, I give you a solution and a disturbance. I can define these occupation measures and terminal measure that satisfy this equation. But what about the other way? What if I find an arbitrary solution to this equation? Does that then imply the existence of a trajectory? Well, it turns out it does. So suppose mu and mu t satisfy the following equation. Then there exists an xs and d, beginning from the initial condition and with a gain k, that satisfies the dynamics everywhere, almost everywhere, and live in the support of mu and terminate in mu t. So what that means is wherever mu is non-negative, that's called the support, and the trajectory actually lives wherever mu is non-negative. So So in fact, where mu is non-negative somehow summarizes all of the trajectory information for my system. Okay? And in fact, this relationship between the two means that instead of studying a nasty, hard, nonlinear dynamical system, I can instead study this really nice linear equation over measures. So what that's going to give me is a nice optimization problem. Suppose I wanted to compute the reachable set of x naught under capital F. What I can do is solve this infinite dimensional linear program, where what I try to do is supramize the support of that terminal measure, so try to find as many trajectories as possible, while satisfying this equation, subject to the condition that all of the measures be greater than or equal to 0. Okay, so again, the support objective basically tries to find as many trajectories as possible that arrive at that terminal set. This equation ensures that I satisfy the dynamics. And this equation ensures that these measures are actually non-negative, because I want them to actually describe the time that a trajectory spends inside of the set. Okay. The important thing here is that this is an infinite dimensional linear program over mu and mu t. So it's clearly linear. This is linear, this is linear, this is linear. Support being linear, well, that's a little hard to see, but it turns out to actually be true. And this is just a positivity constraint, so this is also linear. So the question is, why is it infinite dimensional? And the reason is because I need this equation here to be true for all functions. So now I've done some fancy arithmetic here. I've taken a problem that was seemingly really hard to solve. I've turned it into something that, at least on paper, looks much easier to solve. But the penalty I've paid is by introducing an infinite dimensional number of constraints, or infinite number of constraints. Okay? Well, first, the good news is we can prove that the support of the optimal solution to this problem is actually DFRS, meaning that every trajectory that belongs to DFRS actually lives inside of the support of mu star. So these two things are identical. The other bit of good news is that if I'm given dynamics that are nice, so polynomial, rational, or trigonometric, what I can do is construct a sequence of semi-definite programs with vanishing conservatism that compute a polynomial function, W. Okay, that's a function of ds and k, whose one super level set is actually DFRS. So now what I've done is I've wanted a nice representation for my optimization, or my FRS problem. And in fact, what I can do if I can solve this problem exactly is generate a polynomial function that actually represents that DFRS. Specifically, its level sets represent DFRS. Okay, so one more bit of good news. I can actually take any of the solutions to that sequence of SDPs, any one of them, and it'll also generate a W, and that W will be an outer approximation. That is, its one super level set will be an outer approximation to DFRS. Okay, so this is great. Seemingly, I've taken a really hard problem, transformed it into another seemingly really hard problem, but the good news is I can write down a set of approximations to that really hard problem that are convex, that generate a nice representation for the set that I wanted to construct. Okay, so this is good news. So the next thing I want to try and do is use this efficient representation in order to understand how to generate k-safe. Remember, these are the safe set of gains, and I want to be able to do this very efficiently, because at the end of the day, I want this piece to run in real time. So I can do that DFRS computation offline, but in real time, I want to be able to do this set intersection to ensure the safety of my system. So what we want to be able to do is, if I have an obstacle appear here, I want to be able to figure out all of the gains that could potentially run into this obstacle and eliminate them. So that would look like this set here. If I have another obstacle, I want to eliminate those gains. And another set here, or another obstacle here, I want to eliminate another set of gains. And in practice, what I really want is an inner approximation to the set of safe gains. If I can find that inner approximation, well then at the end of the day, I have a nice way to talk about the safety of my system. And if I can do this in real time, well, that'll be the real win. So I'm going to write down another program that's going to solve this problem. Okay, so given an outer approximating W that's potentially computed offline, and obstacles, what I'm going to do is compute the safe set of gains by solving this program. This is also a linear program. Okay, what it's going to try to do is essentially put a constraint between that W and H. H is the object that I'm going to be optimizing over. Okay, so in fact, what I want is that when I subtract 1 minus W, I'm basically finding the points that are infeasible according to this constraint. And I want H to be less than 1 minus W, meaning that if it's in the reach set, what I want h to be is less than 0 on the set of obstacles that can be reached from this particular situation. Okay? What I'm going to try to do is find the largest possible h on the rest of the gains. And I'm going to ensure that h of k, actually this should be flipped, it should be less than or equal to 1. I want h to be upper bounded. And what we can prove is that this is also a semi-definite program. And in fact, any feasible h to this problem has a 0 super level set that is an inner approximation to k-sig. And that's it. So now, the question is, can this actual optimization run in real time? And the amazing thing is that in practice it can, and this is where the two words discussion begins. So we've run this empirically on a variety of obstacles here. Now again, these obstacles can appear as arbitrary non-convex obstacles. Okay? And I'll talk about, if offline, how we can actually solve this semi-definite program, even if it's an arbitrary non-convex obstacle, still using nice convex optimization. So this is the number of obstacles, and we can actually run this set intersection. We ran this over 10,000 different obstacle configurations. And in this instance, it basically grows fairly linear. We have a really efficient implementation for this, but in fact, this is really, really fast. When we're doing trajectory planning on a car, we're going to start operating about at a 1.5 second time horizon. So this set intersection can actually run really efficiently given that horizon. The next question is, how do we actually choose that capital T, that thing that was defining the DFRS, correctly to ensure the safety with this bounded planning time? Okay. So what we can do is suppose tau plan is the planning time for this problem. So that is the amount of time it actually took to run this set intersection. Haven't proven it's bounded, just empirically observed that it's bounded. Okay, so that's the little bit of a gap here. But let's assume that for the moment, tau plan is actually bounded. Let's call tau stop the maximum stopping time for any state in my smaller state space under a family of braking maneuvers. And remember, these braking maneuvers correspond to an input that's being followed by that lower dimensional system, and I understand that gap between that low dimensional system and high dimensional system using W. And finally, let's assume that I have a sensing time horizon. That's the minimum time required to cover the sensing distance. So suppose I have LiDAR operating. That LiDAR has some window upon which it's operating. And suppose I can travel at 60 miles per hour. So how long would it take me to cover that sensing time horizon given this information? Okay, so assume that I have these pieces of information. Well, what I'm going to do is I'm going to write a theorem that's essentially going to ensure the safety of my autonomous vehicle under these assumptions. I'll make one more. That assumption is that all the obstacles are static. And again, this is a big assumption. Obviously, it's not true. But we'll talk about next how we can generalize this assumption. The next bit is not really an assumption. It's just how we operate. We're going to assume that we can compute a controller while executing the controller generated in the previous step. So we're basically running in sort of a pipeline fashion. So we compute the controller that we are now executing. So we compute a controller that while we're computing this controller, we're using the controller from the previous step. So that's what this is saying. So suppose we choose a t that satisfies these restrictions, and we have a safe trajectory over this time horizon. Well, in fact, then you can prove that there's a safe trajectory for all time. Okay, and it's basically a one-liner. It's not too hard to prove this. And in fact, if you look, I guess in a few hours, you'll see this version up on arXiv that you can take a look at how this works. So what we decided to do, despite having this theorem, is actually to see how well it performed. Okay, so we chose tau plan to be about 0.5 seconds. So again, we operate about an order of magnitude faster than that, but we wanted to be a little bit conservative. We made tau sense, I think, about 1.5 seconds. And we made tau break about 0.5 second as well. We ran this over 10,000 different runs, and we found that all of them are safe. So in this blue here, for example, is the sensing horizon. In green are these reach sets that we're computing, and this is the trajectory. And you can see every star is where we're planning. Okay. Now, for this model, we use the Dupin's car as our higher dimensional model. And for the low dimensional model, we actually use something that's a Luger tire model. So we use something a little bit fancier than the unicycle model to actually verify that this was correct. Okay, so it's not as accurate as a car sim model, but it's quite a bit useful. So in fact, we've actually used that in the first set of videos that I showed you where we were running that MPC. The way that we do that trajectory design for the MPC actually begins with something that looks like a Luger model. So this is pretty realistic, high fidelity model. Okay, here's another example where now we have some roads. Okay. And again, I should mention all of this is running in real time. So we're not slowing this down. It's basically running, I mean, my computer may be slowing it down, but in fact, we do all the computation in real time. Okay. So notice in this instance, basically, and let it replay again. So come on. Okay. So what you're going to see is at this point, it could make a right turn here, but basically it follows a trajectory the entire time horizon. It doesn't decide to switch a trajectory halfway. And that bit of conservativeness is actually a problem for us. Okay. What we want to be allowed to do is somehow use that set description and allow ourselves to switch arbitrarily between controllers during that time horizon while ensuring that each of the sets that we're generating are safe. Okay, so that switching, which we're not doing here, we're following a trajectory for the entire time, is kind of a place where we have conservativeness that we want to try and avoid. And in fact, in this instance, I'm just solving a nonlinear optimization to solve this problem. I'm not doing anything fancy. Despite having that nice representation and performing the set intersection, the moment I have that safe set of gains, all I'm doing is just selecting somehow between that safe set of gains. What we'd really like to be able to do is optimize over that safe set of gains in a nice way. And maybe that'll be the next part of my talk, although I'm noticing I'm running out of time. So maybe we'll get to that slowly. So we're working on a small-scale application. So this is a car built by some undergrads in our group. So they've basically thrown all sorts of sensors on here. They have a single-shot detector running in real time. And basically, we've already started doing experiments on this. My students started this week, and it actually works fairly well. But the videos are not up yet, and you'll see why well, I'll talk about that offline maybe. The other thing we're looking at is how can you actually do real-time prediction where obstacles are moving? And the first thing here is that we really do need ways to generate real-time predictions of where people can go. So in fact, we have a nice paper in RAA Letters where we're actually generating real-time predictions using context-based information. And we can prove theorems about how fast this operates and actually say something about being able to compute these objects in a nice way. I'll mention, just sort of casually, that we've been applying these types of methods also to understand human biomechanics. So one of the things we're really interested in is trying to predict the stability of motion. So this is me. This usually used to be a picture of Ruzhna, but now I guess I'm the PI. So what you see here are basically me doing a sit-to-stand experiment, and I'm being pulled by cords here. What we want to do is look at people going from sit to stand and build that reachable set for them, going from sit to stand, and understand the set of perturbations that can be applied and still have them get from sitting to standing safely. And this is a way for us to understand how stable a person is. And if we can run this type of optimization effectively, well, basically we have something that can sit at home and be able to evaluate you all of the time and figure out when you're running into a problem, not just when you fall and hurt your hip. In fact, we've done some work here where we've actually built these models in a nice way. And in fact, we've actually validated them. So this is going to be what the validation looks like. So this is one slice of the state space. This is the trajectory. And this is the basin, or the FRS that we're computing. So all of these states in here are basically able to converge to this trajectory over time. And in fact, what we did was we started applying these cable perturbations. And we could predict when this cable perturbation would lead to a fall for the person, or when they wouldn't actually be able to stand up. So in fact, in this instance, this perturbation pulled them outside of the set. And in fact, in this instance, this person was not able to stand up correctly. So in fact, this measure here is actually able to characterize the stability of the individual in a nice way. So one of my students did all the work on the actual cable pulls, but one of our collaborators here actually did some of the work on building these stability basins in a nice way. So I'll also mention we've done some work here on being able to apply this to battery control and other things as well. Okay, so these methods are actually quite powerful, and having this representation in a nice way can be really useful for a variety of different problems. So I was going to talk about basically trying to figure out how to reduce that conservativeness by basically trying to figure out a way to switch between controllers in an effective way. Okay? And that was going to be this portion of the talk, but I'm noticing I only have 10 minutes. Should I pause here and ask questions, or wait for questions, or should I continue? Continue? Okay. All right, so what we're going to try to do is formulate this as a hybrid system. Okay, what I'm going to try to do is basically have a hybrid system that's switching between these different controllers and try to figure out a way to solve this hybrid system optimal control problem. Where basically what I can do is I select a gain, and then I get to select this gain over and over and over, and I want to be able to figure out a way to hold on to that safe set of gains and perform that switching bit of the optimization in a nice way. So first I need a definition of hybrid systems. Everyone here is from Berkeley, so you've probably seen this definition before. So I have domains, I have vector fields, I have control inputs, I have a graph that describes how I switch between these, I have a set of guards, I have a reset map that describes how I transition from mode to mode. So the perfect example of these systems are walking robots. Walking robots are things that walk around. The moment they touch the ground, their dynamics have to change because they've made contact with the ground. So their dynamics reset and begin evolving in a new mode. where now, for example, if I put my foot down, in this mode, I'm in a lower dimensional system, so I have a different vector field that describes how I move. We're going to make an assumption here. That assumption is that we have no z node. Okay? So that means that we don't switch infinitely often. Okay, so let's talk about an execution of the system. So here's a perfect example. It's a walking robot. I begin from some initial condition. I belong to some dynamics, F1. I evolve. Maybe I put this blue foot on the ground. At that moment, I satisfy a guard. That guard causes a transition. I reset my condition here to a new mode. And then I continue evolving according to a new dynamical system, F2. Okay? Until some final time. So what we want to be able to do is solve this optimal control problem. And in practice, we have a running cost, we have a final cost, we have an execution of our system, and basically what we're trying to do is select an input and select an initial condition. The reason we want to be able to select an initial condition is because our gain space is something that's fixed, right? It's k-safe. It's not moving around. And essentially, I want to select a gain from that k-safe to ensure that I solve this optimization problem. So this is the optimal control problem for hybrid systems in sort of full generality. Okay? So why is this problem so hard to solve? I spent my career here at Berkeley working on versions of solving this problem. It's very hard. It's because of the lack of derivatives. The lack of derivatives, basically describing the transitions between these different systems, means that generally speaking, I have to solve this using combinatorial methods. So people have done this for walking robots for a long time. So they do things like fixing the switching sequence. They relax the notion of contact. They assume the contact sequence is known. All of these things have problems because basically there's then a gap between what the real system is doing and what these systems are actually doing. And in particular, what the optimal solution to the problem is doing. So what we're going to do is we're going to use the measures to solve this problem as well. And the measures satisfy two important requirements that are going to make it easy to solve this problem. So first off, suppose I have a running cost where I'm integrating over dt. Well, it turns out what the measures do is basically take this object, and now I'm integrating, instead of from 0 to t, I'm integrating over the whole space. So in fact, this is a measure that's defined from 0 to t, di, and u. Okay, what this has done is this was a nonlinear running cost, but here, this is a linear function, right? Because the measure is basically acting linearly with respect to h. In fact, to emphasize that linearity, I'm going to write this inner product again. And in fact, the same thing is true for that terminal cost. I can write it in this way, where basically I'm now integrating over a measure. And again, I can write it in this nice way. As we saw earlier, there's a nice relationship between these trajectories of the systems and these measures. They satisfy this equation. Okay? But now, our dynamical system is a little bit different. Earlier on, we were talking about a dynamical system in a very specific way. That dynamical system was control affine, meaning that the disturbance, which was something like the input, appeared linearly in the problem in a way. But now, my dynamics are completely arbitrary. I can't specify anything about my dynamics. This is like I'm trying to solve the low-level trajectory design problem, and I know nothing about the design space, okay? Meaning the control space. It could act in any possible way. So in fact, to prove this converse result, I need to assume something about Fi. And the thing I need to assume is that Fi is actually convex over mu. Okay? In this instance, I can actually show that these two solutions are exactly the same. So the question is, how do I now represent this when it comes to hybrid systems? And the way that we're going to do that is by basically applying a really simple idea. So I have this terminal measure. I have an initial measure describing all of my possible initial conditions. What I can do is add measures at my guards, describing trajectories that leave the system. Okay, and I'm going to describe a new measure that's going to be called push-forward measure. I'm going to speed up a little bit. That's going to describe measures arriving at my new mode after reset. Okay, this is still a linear equation over measures. And in fact, what I can show is that my trajectories satisfy this new equation. And in fact, I can prove that as long as my dynamics are convex, that basically they're going to still satisfy this linear equation. So there's no gap between my two systems, my two PDEs. Okay? So now I have my optimization problem that I originally wanted to solve. Okay, well, now what I'm going to do is I'm going to replace that h here with an hj. I'm going to define a new running cost for each of my modes of my system. Okay, so that's going to be a linear object. I'm going to replace each of these guys with their measures. So I'm going to write down this object here. And now I need to replace my execution, and I'm going to do that with this nice linear equation. So now I've taken a combinatorial problem, a really hard optimal control problem, and replaced it all with a really nice optimal optimization problem that's infinite dimensional. This equation still has to be satisfied for all possible functions. But again, I can prove lots of properties about this and develop a nice way to solve this using STPs. So in fact, the first thing is I can prove that this optimal control problem and this LP problem that I have here basically satisfied this requirement when I make no assumptions about the dynamics. So this LP is always computing lower bounds to the original optimal control problem. And in fact, when this running cost is actually convex, they're identical. Okay? And again, I have this really nice property that there is no gap between them as long as I assume my dynamics are convex in U, and I assume my running cost is convex in U, which is usually true for most of the systems we're interested in. Okay? And I can synthesize a controller and find the initial condition as well by solving a sequence of STPs. So we decided to apply this just to show what it looks like. We're still working on applying this to the car system. But the first example we're looking at are these walking robots. This is a really simple model of walking. It's called a slip model. Spring-loaded inverted pendulum. Okay. This problem is so simple, but it's actually really hard to solve for what's the optimal way to even run to a point. Suppose I wanted to optimize how much energy I was consuming. Basically, we have to fix the mode structure. If I give you a different time to resolve this problem, it's really hard to solve. Okay? But in fact, we're able to solve this problem using these STPs. And these are different orders of relaxation of that STP. And this is a nonlinear optimization solver that we use to basically solve the same optimization problem, just to benchmark our performance. So we're able to find the solutions. So this is relaxation order 4, 6, 8, and they run really quickly compared to this guy, which takes a really long time. Seconds there, it's a typo. In any case, notice that they're generating lower bounds to the true optimal cost, and you can prove that about the relaxation. So this is really great. And in fact, what we can do is use this guy's solution to seed this optimization problem and have it run quicker. Okay? And in fact, we've done that. And basically, by using this guy's, even the relaxation order 4, we can get a really great solution from this nonlinear solver, which can operate a little bit quicker given that seed. So we're actually using this to do gate design for this robot. And we're actually applying it now to actually do that vehicle control. But again, we want to think about how do we bound the time of operation. And this gets to my last point, which is by transitioning everything into an STP, something that's convex, we can start thinking about how do we bound that computation time. And that's what our group is now starting to think harder about. It's a hard problem, though. So what I'll mention is that we've spoken about how to do this efficient representation for real-time trajectory synthesis. This is Shreyas and Sean. They're the ones who did that. Patrick and Shannon are the ones who've been doing that cable study. Henry and Owen. Owen's actually a high school student. He's the one who wrote that paper that did the real-time predictions. He's amazing. Okay? And Hung Chung and Niels here are the ones who've been working on that hybrid optimal control problem. And all of this work was supported by NSF and another NSF project in Ford. So thank you.